Howdy Calc BC, welcome back. We're back in the virtual library here just to do a short video for you on alternating series. So as we're continuing our work through on series and convergence, we're going to be looking at a couple of different tests and different kinds of series along the way. We've looked at P-series, we looked at geometric series. Today we're going to look at something called an alternating series, and an alternating series is a special kind of series. Unfortunately, and through a very critical error on my part, I've come home without my trackpad for making this video. So I've written a bunch of stuff out by hand, and I'll be using the cell phone here as a sort of a modified version of a webcam to hopefully display some stuff for you and get that on there. So if you haven't already, if you wanted to come in next week, I'm going to be putting the link for signups back in Schoology. If you have already signed up, cool. If you're not able to get it done this week, I totally get that. And if in the future you decide you do want to do that, I think that would be fantastic. But for right now, we're going to try and get this thing set up to go. I know the video probably just jumped right over all that, but all of a sudden I was having massive technology problems right here. Anyway, let's get over and check out some alternating series. All right, I'm gonna move over to my webcam. And so what we have when we have alternating series, then the name kind of implies that we're just seeing a series where the terms are alternating between positive and negative. And for us, recognizing that we have an alternating series is really quite nice because it will help us in determining the convergence divergence behavior pretty easily. So if you kind of zoom in a little bit here at the top, I've got that the series -1 to the n a sub n and -1 to the n plus 1 a sub n. Those are alternating series because you can see they would bounce between being a positive and a negative term. I see what's going on, guys. The virtual background's causing some problems. Let me turn that off so we don't have that. There we go. Apologies. So as you can see, in both cases, all we have to show are two things. One, we have to show that the limit as n goes to infinity of the terms a sub n, so ignore the alternating negative sign, as long as the limit of those terms is 0, and that the n plus 1th term is always less than or equal to the nth term. So the 7th term is smaller than the 6th term, the 8th term is smaller than the 7th, so on and so forth. And that's got to be true for all n. Now, I put a little star there and said, see the note on 590. Again, Dr. Larson hides some pretty good stuff in the details. This only has to be true, this inequality here, for a sub n plus 1 or greater or less than a sub n after a certain point, right? Again, we don't care what happens in the first finite set of terms in a series. It's the infinite part that we're interested in. And only after we get past some capital N number of terms does this inequality have to hold. So I know the theorem says for all n, but in practicality, it's only that at the end, we have some sort of series like this. So you might remember our harmonic series, 1 over n. Well, what happens if I turn it into an alternating series, which I've done here? So I have -1 to the nth power over n. It's called the alternating harmonic. Well, notice if you take out the -1, then we're just looking at the terms 1 over n. And as n goes to infinity, those do in fact go to 0. Also, look, 1 over n plus 1 is definitely less than 1 over n for all n greater than 0. So we have an alternating series where the limit of the terms is 0. The n plus 1 term is always smaller than the nth term. So this series, when we turn the harmonic series into an alternating series, it becomes a convergent series, even though I know the harmonic series doesn't converge. Okay. In my second example here, I've got n goes from 1 to infinity, -1 to the n plus 1 power, and then my terms are n plus 1 over n. And here are some terms: 2 over 1 minus 3 over 2 plus 4 over 3 minus 5 over 4. And I want you to notice something, that in those terms, the oh my, the n plus 1th term is definitely smaller than the nth term. N plus 1 over n plus 1 is definitely going to be smaller than n plus 1 over n. But what happens as n goes to infinity to n plus 1 over n? You get 1, not 0. So our original series here is actually a divergent series, even though it is an alternating series. So that's the alternating series. There's a couple of interesting things that come in alternating series. One of them is we can start to talk about a remainder factor. Okay, now a remainder factor comes into play when we start saying, well, okay, I know this is an infinite series, but maybe I don't want to sum the entire thing to infinity because, that might take literally forever. Well, if you stop short of infinity, okay, so we have -1 to n, a sub n converges, okay, the error in using the nth partial sum, okay, s sub n, to approximate the entire sum is called the remainder, r sub n. And r sub n is always less than or equal to the first excluded term or neglected term. Okay, so that is, look here, s minus sn, that's your remainder, right? The whole sum minus the part that we used gives us a remainder. And that will always be less than the n plus 1th term. So it's contingent upon the series being convergent, of course. But that means, in a series like example 3 here, I've got -1 to the n plus 1 power times 1 over n factorial. Okay, that is definitely a convergent alternating series. Okay, so we're going to approximate this by using the first 6 terms. So here's what I did. S6, well, that's 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1. Okay, you get the idea. And at the end here, I added all that up and I got 0.63194. Now, that's the 6th term approximation. It's not exactly right. So to find out, well, okay, how close are we? I use the remainder theorem. Look, R6 is less than or equal to the 7th term in the series. So it's 1 over 7 factorial, which is 1 over 5040, or approximately 0.0002. So by using the first 6 terms, I actually get really close to the full sum. It's just, I know there's going to be a little bit of error because I've stopped short of infinity. That's the remainder term. We're going to see other types of series and we will be looking at the remainders. That's going to be part of the error analysis that we're going to do. So this is kind of our first chance to really talk about, well, what does that remainder look like? And we can do that pretty easily in alternating series because it's always just the next term in the series is the upper bound of the error. The other thing that we finally get to see now that we're talking about alternating series is something called conditional convergence versus absolute convergence. Okay, here, zoom out a little bit. Okay, so a series, okay, now I'm shorthanding it here. I'm not putting the limits on the inequality there. A sub n is absolutely convergent. Okay, so it converges absolutely if the absolute value series also converges. Notice a sub n, this is the absolute value of a sub n. If absolute value of a sub n converges, we say the series converges absolutely. We say the series a sub n conditionally converges if the sum a sub n converges and the sum of the absolute value series is divergent. So in other words, when you put the absolute value signs on it, you get something that doesn't converge, but it converges as long as it's alternating. It's conditionally convergent. Now, this actually gives us a really handy way to talk about series convergence if we can prove the absolute value series converges. This is theorem 8.16. It's on page 593. If we can prove the absolute value series converges, then we know the underlying series also converges. So that's what we really wanted to get to here was, well, if we prove the absolute value convergence, absolute convergence implies regular old convergence for our series. And I've got an example here for you. Obviously you could think about our harmonic series. The harmonic series was not convergent, but but the absolute, so I'm sorry, the alternating version of it was convergent. So there's a conditional convergent series. Um, here's an interesting example. I grabbed this one out of the book. It was the sum from 0 to infinity of -1 to the n factorial over 2 to the n. I thought it was interesting because they started at 0 in this one. Um, and notice that gives us 0 factorial over 2 to the 0, 1 factorial over 2 factorial, or to the first, sorry, 2 factorial over 2 squared minus 3 factorial over 2 cubed. That's actually a divergent series just right out of the gate. And it's because of the nth term divergence test. Don't forget about nth term divergence test. Yeah, this is an alternating series. It's not going anywhere because the limit of the terms is not 0. Now I see that I've actually written I've written something down incorrectly. The series has to start at 1, not infinity, because otherwise, or not at 0, because you'd have infinity for your first term. So here's a great example of a conditional convergent series. So it's -1 to the n over root n. I've written out a few terms of the series here. Now this meets all the criteria for convergence while it's alternating. The limit as n goes to infinity of 1 over root n is 0. And 1 over the square root of n plus 1 is definitely less than 1 over the square root of n for all n. So this is a convergent series. Okay. Conditionally convergent series. Why is it conditionally convergent? Well, if you put absolute values on there, notice what happens. You get 1 over square root of 1 plus 1 over the square root of 2 plus 1 over square root of 3 plus 1 over 4. Guys, that's just the p series 1 over root n. And with the p series, with p equal to a half, anytime the power is, less than or equal to 1, we know is divergent. So this is a great example of a conditionally convergent series, much like the harmonic series from earlier. Okay, it converges as long as it alternates. As soon as you put that absolute value sign on there, though, it's no longer convergent. That means it is conditionally convergent. So there we go. Alternating series. Oh, green background now. Alternating series are great. They're not super complicated, and I like them because it's nice and easy to prove convergence with them, as long as you can prove the limit as n goes to infinity is 0, and that eventually the n plus 1th term is always going to be smaller than the nth term. And I think that's about it for today, guys. So thanks so much for checking out the video. Uh, and sorry about not having the trackpad here to do that. Obviously, I have to think that ahead a little bit more carefully in the future. All right. See you guys in class. Oh, don't forget to sign up on the Google form. It should be posted in Schoology now. All right. See ya.